Chapter 7, we've talked about work. Next topic in Chapter 7 is work due to a variable force, but I'm going to skip past that. As I sometimes do, I'm going to take the topics out of order from where they are in the book, and I'm going to go to power. So, what is power? Well, we exert a force on something and we make it move some distance. And so we define work as force times distance. Now, as we'd indicated, really it's going to be, F dot X, or in particular, I'd indicated it'd be like F dot dx. Okay. But this is work. Okay. But the next question is, okay, so if it doesn't move, you haven't done any work. It's like those of y'all that drive up and down 35, and you drive by and you see a bunch of workers standing around and a big pile of rocks and then big yellow machine. You drive by the next day and the workers are still there, the pile of rocks is in the same position and the machine's in the same position, and so no work was done all day because nothing was moved. And so this week, again, an idea of what we're doing with work. But the next question is, if you do see progress being made, you want to know how fast is work happening, and that is power. So power is defined as the rate of change of energy. Now remember, work is change in energy. So power is the rate of change of energy. In physics 2, we'll talk about dE dt, the rate of change of energy. We'll think about power in that kind of fashion. But for right now, we're just going to think about power as dW dt. So average power is going to be work over time, or literally just change in energy over a time interval. So that's the average power. Well, this kind of gives an idea of units. So work is in joules and time is in seconds, so a joule per second is a watt. Remember, a joule is a kilogram meter squared per second squared. So a watt is going to be a kilogram meter squared per second cubed. Okay. And so when I was a student, I actually found it helpful to have when I was doing homework or things, a sheet of paper and just list what all these units are and what the units represented and what they were composed of. That really helped me as a student. Okay, so now we have a definition of power. Okay, so power, the rate of change of work. Well, let's look at a special case of power. So let's look at a special case. So we have an object, it's moving, and we have a constant force acting on it. And so that means we're making it move. Now, that would be, for example, a rocket engine here, with constant thrust. It could be an aircraft engine, so we can have an aircraft engine pushing it at constant thrust. We could have a variety of things here that could be doing this. And so what we want to do is we want to look at this and say, okay, so we've got constant forces here. What would be the power? Okay, again, we could just pull an object along. There's friction here. So how much power am I having to exert to pull at constant speed? With a constant force. Okay, so power is the rate of change of work. Okay, so that's the derivative of F dot X. Now, you know how derivatives work. That would be the derivative of F dot X plus F dot dx dt. Well, if we have constant force, that term is 0, so the power would be F dot V. Okay, so that gives us an example of power for constant force. Okay, and so now we'll just do a few examples of this. We said that power is measured in watts. Okay. We said a watt is a joule per second. We said that means that a watt is a kilogram meter squared per second cubed. Okay. Well, there's another unit here of power I want to mention, and that is that for historical reasons, we use something called a horsepower. Horsepower is defined to be 746 watts. And so what you would do is you often, for example, have motors, and you might have a motor. You might have a motor here that has a power output of 12,500 watts. And so, but you know, that's kind of a big number. We don't really like to write really big numbers if we don't have to. So what we do is we would say that 746 watts is a horsepower. So you divide that by 746 watts, and that's 16.8 horsepower. So that'd be a little bit less than a 17 horsepower motor. And so this, numbers that are in that range are far easier to mentally visualize than numbers in that range. And so that's why often we pick whatever units make this. Now, 746, this flies right in the face of the standard convention of the metric system, and that is all base 10 stuff. But we still use horsepower as a very, very common sort of unit. So something else interesting to sort of think about, and that is when you get billed for electricity, what do you pay for? Well, obviously you pay dollars and cents, but what are you actually paying for? And that is kilowatt hour. So what is a kilowatt hour? It's exactly what it sounds like. A kilowatt times an hour. So that means it's 1,000 watts times an hour. An hour is 3,600 seconds. Now we know that a watt is a joule per second. So that means a kilowatt hour is 3.6 million joules. Okay. Now, you get your electric bill and you got hundreds of kilowatt hours, maybe thousands of kilowatt hours, and you got $100 or so, several $100 electric bill, and it's like, oh my gosh, this is expensive, and so forth. On the other hand, I think it would be a great marketing ploy for the electric company, because they could bill you for like 10 billion joules worth of energy, and you're only paying a few $100s for it. It's like, wow, what a fantastic deal. I get billions of joules for only a few $100. And so anyway, but that's like I said, we typically are used to keeping track of things in units that are such that we can visualize something. Visualizing billions is actually kind of difficult.